Many of us can recall several tragic events caused by earthquakes: the Christchurch, New Zealand earthquake sequence in 2010 and 11, the Tohoku, Japan earthquake in 2011, the Haiti earthquake in 2010, and the Mexico City earthquake in 1985. In Christchurch, there was widespread liquefaction damage. The Tohoku earthquake generated a devastating tsunami, and the Haiti earthquake resulted in severe damage and loss of life. In Mexico City, over 420 buildings were destroyed due to the massive ground motions that occurred. To begin to explain what happened in Mexico City, let's conduct a lab experiment. In this experiment, we have 3 pendulums, each of the same mass, each has a different height. They're all fixed to the same base. We're using a dynamic shaker to excite them, and the direction of shaking is going to be horizontal. First, we have minor shaking of all 3 pendulums at a frequency of 10 Hz. Heavy shaking of the shortest pendulum at 7.6 Hz. Heavy shaking of the mid-sized pendulum at 4.7 Hz, heavy shaking of the tallest pendulum at 3.9 Hz, and at a frequency of 1 Hz, there's minor shaking in all 3 pendulums. Let's look at the results of our experiment. Each of the pendulums responded at a specific frequency based on the height of the pendulum. That specific frequency is known as the resonance frequency. When we plot these relative motions versus frequency, we see an envelope that summarizes how the pendulums responded to shaking over a range of frequencies. Our lab models responded at higher frequencies than those produced in the Mexico City earthquake. However, most of the buildings that failed in Mexico City were 10 to 14-story buildings with resonant frequencies that matched those produced in the earthquake. Now let's conduct a field experiment. We have a 1.7 meter reinforced concrete structure. To excite the structure, we'll use our shaker truck T-Rex, capable of generating shearing ground motions from 8 to 80 Hz. In plan view, our shaker is spaced 7 meters from our structure. We have 5 sensors placed on our column and 2 placed in the soil between the shaker source and the structure. The direction of shaking is perpendicular to the structure, which will generate shear waves. We will be using an upgrade sine sweep to excite our structure. To demonstrate this experiment, we have 2 angles of our shaker source, an angle of the structure, and the time histories from our 5 sensors will play out on the graph. Based on our model of the structure, there is coupled rocking and sliding with a peak response at 16.6 Hz, which compares well with our experimental results. In summary, in practice today, the geotechnical engineer provides the response spectra of a site to the structural engineer, who will ensure that the building does not have resonance in the frequency range excited by the earthquake, or is built to withstand the shaking.